Hello, ma'am. Good morning. My name is Shreyas. My registration number is 24BCE1882. This is my DA3 video for computer networks courses. The topic I have chosen is RTT delay analysis using Wireshark. I have analyzed RTT under three different conditions: low traffic, medium traffic, and high traffic. In this video, I will explain what RTT is, how I capture the traffic, what my results are, and show you my blog, GitHub repository, and RTT graphs. Let me begin. So, what is RTT? First, let me explain what RTT means. RTT stands for round trip time. It is time taken for a packet to travel from the source to a destination and back to the source. Let me give you an example. When I send a request from a laptop to Google server, the packet travels from a laptop through my Wi-Fi router to the internet and reaches Google server. The Google server then sends a response back through the same path to my laptop. The total time from when I sent the request to when I received the request is called the round trip time. RTT is measured in milliseconds. 1 millisecond is 1,000th of a second. Lower RTT means the faster network and better performance. Higher RTT means slower network and congestion or delays. RTT is very important for online applications like video calls, online gaming, video streaming, web browsing, etc. If our RTT is high, you will experience a lag in our games, which you have noticed, or delays in the video calls. So, measuring and understanding RTT is critical for network performance and analysis. Now, let me explain how I conducted the experiment. So, for the experimental setup, in this experiment, I have used the following equipments and the tools. First, my laptop is MacBook Air M2. This is my primary device for capturing and analysis of traffic. Second, I have used Wireshark. Wireshark is a free and open source packet analysis tool. It allows us to capture and inspect network packets in real time. Third, I use the ping command in terminal. Ping is a simple network utility that sends the packets to the destination and measures the time it takes for the response to come back. I used 8.8.8.8 as my destination. 8.8.8 is Google's public DNS server, and it always is available for responding to my ping requests. My internet connectivity for I have used my mobile hotspot instead of hostel Wi-Fi. Why? Because hostel Wi-Fi blocks the ping request and many other protocols. The mobile hotspot has no such restrictions, so all my ping requests went through successfully. Now let me explain the procedure I followed. So I captured the traffic under three different conditions: low traffic, medium traffic, and high traffic. For low traffic, I have used the command ping c 58.8.8.8. Let me show you in the terminal. So if I scroll the terminal, here you could see what is my command. Ping c 3.8.8.8.8. So here 50 means that I have sent 50 packets. Each packet is sent 1 second apart. So this command took 50 seconds to complete. Now for medium traffic, I have used the ping C 500 8.8.8.8. So what does this mean? This means that this sends up 500 packets and took about 8 to 9 minutes to complete. And here comes the last one, that is heavy traffic. So what happened in heavy traffic is I used the command ping C 2000 8.8.8.8. This sends 2000 packets and took about 33 to 34 minutes to complete. While each command was running, I have captured the traffic in Wireshark. In Wireshark, I selected my Wi-Fi interface and started the capture. After each command finished, I stopped the capture and saved the file. I saved three files: low traffic.pcapng, medium traffic.pcapng, and high traffic.pcapng. Then I analyzed these files to measure the RTT values. Now let me show you my results. So for here are my RTT results. I'll show you in my GitHub. So Mm. Yes. So my RTT results for all the three traffic conditions are: for low traffic, there are 50 packets. The minimum RTT was 52.8 milliseconds. Here is the fastest response time that was recorded. The average RTT was 86.5 milliseconds. This is the total response time. The maximum RTT was 126.4 milliseconds, and this is the slowest response time. Packet loss was 0% in the first one, meaning all 50 packets were successfully sent and received. For medium traffic, it was 500 packets. So this was even slower than the low traffic. And for the uh, medium one, the packet loss was 0.4%. And again, for the heavy one, the packet loss was 0%. So packet loss was 0%, meaning all 2000 packets were successfully sent and received. What do these results tell us? First, average RTT remained stable between 86 to 98 milliseconds for all the traffic conditions. This means normal network performance is consistent. Second, maximum RTT spikes increased significantly with traffic load from 126 milliseconds to 833 milliseconds to 1523 milliseconds. This provides that the network condition causes severe delays. Heavy traffic can also cause delays up to 1.5 milliseconds. Now let me show you my blog where I have documented everything. This is my blog. I've published my complete DA3 documentation on blogger.com. Here's the blog title: DA3 Network Parameter Analysis RTT Delay using Wireshark. First, there is the introduction section. I have explained what RTT is and why is it important for network analysis. Then are the objectives. Objective one is to capture the network traffic under low, medium, heavy conditions using the terminal commands. Second is to measure and compare the RTT values across different traffic loads using Wireshark. And third is to generate 20 graphs showing RTT variation and analyze the relationship between traffic load and latency. Next procedure section. I have explained the commands used for low, medium, and heavy traffic. Next is RTT values summary with summary table. Here you can see the minimum, average, and maximum RTT and packet loss for all the three conditions. Next are the screenshots with the inferences. I have added 13 screenshots and written 3 to 5 lines of explanation below each screenshot. Here you can see this. For inference one, the screenshot shows TCP filter applied to low traffic capture. Only TCP packets are displayed, filtering out other protocols. This helps us in focusing on the packets relevant to the RTT analysis. The filter bar shows TCP as the active filter. Second one is the RTT graph for the lower traffic, consistent values between 52.8 milliseconds to 126.4 milliseconds. The y-axis represents the RTT in milliseconds and x-axis represents the time in seconds. The graph indicates stable network conditions with minimal variation, showing the low traffic does not cause congestion. Inference 3. The IO graph for the low traffic shows the packet rate over time. The x-axis represents time in seconds and y shows the packets per second. Low traffic generated approximately 10,000 packets in 50 seconds. The graph shows consistent packet flow without major spikes. Inference 4 is the terminal statistics for the low traffic show. Minimum RTT of 52.8 milliseconds, average RTT of 86.5 milliseconds, and maximum RTT of 126.4 milliseconds. The packet loss is 0%, indicating a stable connection. These values serve as the baseline for comparing the higher traffic conditions. Similarly, it goes on for all the three packet captures. And these are the 20 inferences. Low traffic RTT range from 52.8 milliseconds to 126.4 milliseconds with average 86.5 milliseconds. Medium traffic RTT range for 44.7 to 833.3 milliseconds with average 98.3 milliseconds. Similarly, for heavy traffic, RTT is from 38.8 to 1523.9 milliseconds with average 93.8 milliseconds. Heavy traffic showed the highest RTT spike of 1523.9 milliseconds, that is 1.5 seconds. Packet loss was 0% for heavy and low, and zero point 0.4 for medium traffic. Low traffic captured approximately 10,000 packets in 50 seconds. Similarly, for medium, 25,000 packets for 8 minutes and 17,605 packets in 34 minutes. RTT increases significantly during network congestion as seen in heavy traffic. Wireshark effectively captures RTT for ICMP ping traffic. TCP RTT graphs work best for TCP traffic. ICMP requires different analysis. Mobile hotspot requires different and better connectivity than hostel Wi-Fi for experiments. RTT variation, that is jitter, increases with the traffic load. Terminal ping statistics provide accurate RTT measurements. Wireshark IO graphs show packet rate variation over time. Capture file properties give overall statistics including average packets per second. Different TCP streams show different RTT patterns in the same capture. Switch direction option in RTT graph shows RTT from different and opposite perspective. ICMP filter clearly shows that the ping request and reply pairs for RTT cancellation. So therefore, this experiment proves that RTT is directly affected by the network load and congestions. What are the new findings? So medium traffic showed a significant RTT spike of 833.3 milliseconds, while a heavy graph showed an even higher spike of 1523.9 milliseconds. Packet loss was minimal, 0 to 0.4%. So the mobile hotspot connection provided reliable connectivity with 0% loss. So what are the possible recommendations? Used we use the dedicated network tools like iPerf for more control traffic generation. RTT, we can analyze the RTT over different network types like Wi-Fi, Ethernet, 5G, etc. Study the RTT impact on specific applications like video conferencing and gaming. Capture traffic during different times of the day to analyze the peak and the off-peak performance. Where did I use AI in this DA? AI tools like DeepSeek and ChatGPT were used in understanding the Wireshark features for RTT development, troubleshooting ping blocking issues on hostile Wi-Fi, generating the document structure and 20 inferences, creating the block content, and formatting screenshots, providing step-by-step guidance for the traffic capture, debugging issues with the Wireshark graphs and filters. So here are the references. I have used Wireshark Foundation 2024. I have used the user's guide. I have also used the SharkFest Wireshark conference, TCP analysis with the Wireshark, ping command documentation also, and IEEE 2023 network latency and RTT measurement techniques. Acknowledgements. I would like to thank my parents for the constant support and encouragement, VIT Scope for providing a platform and resources, Dr. T. Subulakshmi, my computer networks course instructor and her guidance and clear instructions, my friends who have helped me in troubleshooting technical issues, DeepSeek AI for assistance with documentation, problem solving, and block creation. I'll insert my YouTube link when all this is done. And here is my GitHub repository link. Now I'll just take you to my GitHub. So here is my GitHub, and this is DA3 RTT analysis, and this is a public repo. And I'll show you the screenshots. First is the heavy capture properties PNG. Here it is. These are the properties. Then we go to second one, that is heavy ICMP filter.png. These are the packets. Third is the heavy iograph.png. Here you can see the graph. Then fourth is heavy packet list.png. These two are the pairs, reply and request. This is 90 and this is 89. This is echo ping request and this is echo ping reply. Then comes heavy terminal stats. These are the terminal stats. 8.8.8 ping statistics, 2000 packets transmitted. Then we come to heavy traffic.pcap. This is low.iograph.png. This is the graph for the low one. You can see how the graph is. Yes. Then we come to low RTT graph.png. Here is the RTT graph for low traffic. As you can see, this is the RTT graph. Then we come to the low TCP filter.png. Here are the packets which were transferred that were filtered out by typing TCP in the filter section. You can see this. There are many TCP packets. Then comes the medium iograph.png. This is the iograph for the medium one. Yes. Then comes the RTT graph for the medium one. There is the RTT graph for the medium one. Yes, we have used stream 3 and we have switched the directions. This is why I got this graph. And here is the TCP filter for the medium one. You can also see that there are so many TCP, different protocol packets. Yes. So thank you very much for watching this now and everyone. This is Shreyas Patel and my registration number is 24BCE1882. I hope my explanation was clear. Have a great day. Thank you.